So let's look at circuit B. So circuit B, we want to apply Kirchoff's laws to find the unknown currents. Right? So as before with circuit A, the first thing we'll do is to label our circuit. So we'll label it A, B, C, D, E, and F. Right? Now after labeling the circuit, what we'll then do is to choose the first loop to traverse. So let's choose loop ABCFA. So we're going to traverse loop ABCFA, right? But before we traverse loop ABCFA, let's establish a relationship between the currents, right? So according to the diagram, the 5-volt battery is driving a current I1, which flows through this 8-ohm resistor, and it meets the current I2 being driven by the 3-volt battery at the junction F. So I1 is flowing into the junction, and I2 is flowing into junction F as well. Based on Kirchoff's first law, some of the currents flowing into this junction must be equal to the sum of the current flowing out. So since I1 and I2 are flowing into junction F and I3 is flowing out of junction F, then based on Kirchoff's first law, we can basically say that I1 plus I2 is equal to I3. And that is based, of course, on Kirchoff's first law, right? So we establish a relationship between the three currents I1, I2, and I3, and then we can actually proceed to applying Kirchoff's second law to our respective loops. So we're traversing loop ABCFA, so that is in the clockwise direction. So let's just draw this arrow, show the direction in which we will be traversing the loop, right? So we start at A, and we proceed clockwise. We encounter the 5-volt battery, but this time we encounter the positive terminal before the negative terminal. So basically we're going from a high potential to a low potential. The charge will experience a potential drop, and this EMF will be treated as being negative. So therefore this would be a minus 5 volts. We continue around the circuit and we encounter the 3-volt battery. But this time we encounter the lower potential, that is a shorter stroke, before the higher potential. This is a potential gain, and therefore this EMF will be treated as being positive. And therefore the algebraic sum of the EMFs, sum of E, is equal to minus 5 volts plus 3 volts, which gives us minus 2 volts. So for that loop, the algebraic sum of the EMFs is equal to minus 2 volts. Now let's apply the second part of Kirchoff's first law, which is to find the algebraic sum of all the potential differences across all the resistances in the loop. So once again, we're going clockwise. We start at A. Now the first resistor we encounter is an 8-ohm resistor. But the current flowing through the resistor is I1, and I1 is going in the opposite direction to that in which we're traversing the loop, and we therefore treat I1 as being negative, and the PD across this 8-ohm resistor will also be negative, right? So therefore we have sum of IR is equal to minus 8I1. We continue. We encounter the 2-ohm resistor, and the same I1 is flowing through the 2-ohm, same direction as before. So therefore this is again going in the opposite direction to that in which we're traversing the loop, and the current I1 again is treated as negative, and the PD across the 2-ohm will be negative as well. So this is now minus 2I1. So let's continue. So coming around, we encounter the 1-ohm resistor. And which current is flowing through the 1-ohm resistor? Now, because the 3-volt battery is driving the current I2, which meets I1 at junction F to form I3, when they get back to junction C, the two currents will split. And so I1 will continue flowing back to the 5-volt battery, and I2 will of course flow through the 1-ohm resistor, right? Now this time I2 is going in the direction that we're traversing the loop. It is treated as being positive, and therefore the PD across this 1-ohm resistor is going to be positive. Likewise, the PD across the 6-ohm resistor through which I2 also flows will be positive. And so we get plus I2 plus 6I2. So if we simplify this, we get minus 8 minus 2, that is minus 10 I1 plus 7 I2. And since, based on Kirchoff's second law, sum of E equals sum of IR, we can say that minus 2 volts is equal to minus 10 I1 plus 7 I2. And let's call that equation 1. Good? Now, we have two unknowns in one equation, so we need one more equation to be able to solve for these two unknowns. And to get that second equation, let's traverse loop FEDCF. So we're going to traverse loop FEDCF. So just as before, we identify all the batteries in the loop and we find the algebraic sum of the EMFs. We identify all the resistances and we find the algebraic sum of the potential difference across those resistances, and we equate them and we apply Kirchoff's second law, right? So we're traversing the loop FEDCF. So this time we're going, what's that? Anti-clockwise. So once again, we'll use the this to show the direction. So we're traversing the loop in this direction, right? Anti-clockwise. So we start at F, we go E, and we encounter the, well, 10 ohm, but we're looking for the EMS first. So we come around and we encounter the 3 volt battery. We encounter the lower potential before the higher potential. There's a potential gain and the EMF is treated as being positive. So therefore the algebraic sum of E is equal to plus 3 volts or simply 3 volts, right? So that is the only battery in that loop. So we now check the resistances for the total PDs. So starting at F and proceeding anti-clockwise, we encounter the 10 ohm resistor. The current flowing through the 10 ohm resistor is I3, which happens to flow in the direction that we're traversing the loop, and therefore I3 will be treated as being positive, right? But of course, we know that I3 is equal to I1 plus I2, but we'll write it down first and then we'll make the substitution. So we'll say the sum of IR is equal to 10 I3, and we proceed. Once again, we encounter the 1 ohm through which I2 is flowing, as well as the 6 ohm again through which I2 is also flowing, and both are positive as before because we're going in the same direction that the current is actually flowing. So this gives us plus I2 plus 6I2. So that gives us 10 I3 plus 7 I2. And so what we now have is that sum of E equals sum of IR. So let's continue. So therefore we have 3 volts is equal to 10 I3 plus 7 I2. But of course, we already have our first equation in terms of I1 and I2. And so our second equation should also be in terms of I1 and I2. So we'll just make this substitution. So now we have 3 volts is equal to 10 I1 plus 10 I2 plus 7 I2. When we add up the I2 terms, we get that 3 volts is equal to 10 I1 plus 17 I2. And we call that equation 2. We'll just write down the first equation directly below it. And so we have minus 2 volts equals minus 10 I1 plus 7 I2. That is equation 1. So if we compare the coefficients of I1 and the coefficients of I2, we see that in the second equation, the coefficient of I1 is 10, whereas in the first, the coefficient is minus 10. And therefore, if we add these two equations, I1 terms get eliminated, and we can then solve for I2. So we'll just draw a line below, and we'll add the two equations. So minus 2 volts plus 3 volts, that gives us 1 volt. This is 0. And then this gives us 7 plus 17, 24 I2. So what we have here is that 24 I2 is equal to 1, and I2 is equal to 1 over 24, or we can express it as a decimal. So 1 over 24 So 1 divided by 24, and that gives us 0.042 amperes. Alright, so the current I2 is equal to 0.042 amperes. Now, having found the value of I2, we can then make the substitution into either equation 1 or equation 2 and find the value of I1 and then proceed to find the value of I3. So, substituting the value of I2, let's put it into equation 2. So, according to equation 2, we have 3 volts is equal to 10 I1 plus 17 I2. So substituting the value I2, 0.042 into that equation, we get 3 volts is equal to 10 I1 plus 17 times 0.042. And so we get 3 volts is equal to 10 I1 plus 17 times 0.042. That is approximately 0.71. This is approximately 0.71. That would be volts. And so we bring this over here, we get 3 volts minus 0.71 volts is equal to 10 I1. So 3 minus 0.71, that gives us 2.29. So 2.29 volts equals 10 I1, which means that I1 is equal to 2.29 divided by 10, and that gives us 0.229 or approximately 0.23 amperes. Right? So correct the two significant figures. I1 is equal to 0.23 amperes. Now, as we established before, I3 is equal to I1 plus I2. Now, before we actually proceed to finding I3, let's examine the signs of these two currents and see how it relates to, or how they relate to, the initial directions in which you assume the currents were flowing. Right? So, I1 was seen to be going in this direction, I2 was seen to be going in this direction, and based on our signs, it basically means that the two currents are flowing in the direction we initially assumed, and so therefore we will then add I1 and I2 to give I3, and so I3 is equal to I1, which is 0.23 amperes, plus I2, 0.042. This is 0.23 plus 0.042, and this gives us 0.272 amperes. So therefore I3 is equal to 0.272 amperes, right? So we've applied Kirchoff's laws and we found the magnitude of the respective currents I1 and I2. So let's examine what is happening with the batteries. Now in the question, basically, these resistances, 1 ohm and the 2 ohm, were given as the internal resistances of the batteries, right? So the 1 ohm resistor is the internal resistance of the 3 volt battery, and the 2 ohm resistor was given as the internal resistance of the 5 volt battery, right? Now let's examine what will happen in the circuit if we should basically connect a high resistance voltmeter across each of those batteries and see what the readings will be. Now, we previously met internal resistance, and we saw how internal resistance affected the EMF of a battery while it is actually driving a current to an external circuit. So basically, the equation which relates EMF to terminal PD and internal resistance is given by this. E is equal to VT plus IR, where VT would be the terminal PD across the battery when it is driving the current as when it is a part of an external circuit. So for the 5 volt battery, what we'll have is this. 5 volts is equal to VT plus the current. In this case, the current being driven through the 5 volt battery is I1, and the value of I1 is 0.23. So this is plus 0.23 times its internal resistance, which is 2 ohms. And so we get that 5 volts is equal to VT plus so this is supposed to be 0.23 rather, 0.23. So 0.3 times 2, that's 0.46. And this therefore means that VT is equal to 5 volts minus 0.46. So Vt is equal to 4.54 volts. So what is the significance of this value? This basically means that if you have the circuit and you connect an ideal voltmeter, or a voltmeter which is close to being ideal as possible, that is one with a very high resistance, then the reading that the voltmeter will display is 4.54 volts, right? And this, as we explained before, is due to the fact that energy will be dissipated as heat within the battery due to its internal resistance, right? So there's some lost volts within the battery. Now for the 3-volt battery, using the same equation, we get 3 volts is equal to terminal PD plus its current I2, which is I2 is 0.042 amperes. This is plus 0.042 times its resistance, internal resistance, which is 1 ohm. And so we get that 3 volts is equal to Vt plus 0.042 volts. And so Vt is equal to 3 volts minus 0.042, and therefore Vt is equal to 2.958 volts. So we see that there's no significant reduction in the EMF due to this internal resistance being only 1 ohm and due to it having only a relatively small current flowing through it.